Hi, good morning everyone. Today we start Unit 3 as a part of Introduction to Quantum Technologies and Applications. So far, in the first two chapters, we talked about what is qubits, how we are going to explore. Now we'll explore what is it actually takes to make a real-time quantum computer. Before going to actual concepts, let's have a look on what is quantum computer. A quantum computer uses the qubits that can be 0 or 1 at the same time. On the other hand, a classical computer uses bits 0 or 1 which are based on voltage levels. Come to the quantum computers is concerned, they perform many calculations simultaneously. That's why they promise a massive speedups for complex problems compared to classical computer. Now let us see a snapshots of quantum computers. Many students may imagine a shiny futuristic box, but it is in reality, quantum computer often looks like a equivalent geometries. Like IBM 53 qubit based on the superconductor circuits, Chinese 76 qubit quantum computer which is based on photon, and IonQ 32-bit quantum computer which is based on trapped ion principle. So when you see that a golden cylinder hanging down, that is a cooling system to protecting a fragility in a quantum core. Let us see a quick timeline of quantum computers. That is a recent timeline. In 2019, Google claimed a quantum supervised quantum computer. Their quantum 54-bit quantum device solved a task in 24 seconds that would take supercomputer in 10,000 years. IBM followed with 54 qubits, and the Chinese group built with 74 qubit photonic mission that worked 100 trillion times faster than specific tasks. These are the proof of concept milestones. Still, my specialized problems are going to face, not a general purpose computing, but they have shown how rapidly the field is programming. By 2030, IBM even plans to for millions qubit missions. By seeing this, that is the rapid growth of quantum technologies. Now let us see what is required. But to build a quantum computer, we need several key components like qubits, which are the building blocks of information, quantum gates, operations that change qubit states, quantum circuits, sequence of gates that form an algorithm, measurement system to convert the quantum information into a classical output, a control electronics to precisely manipulate qubits, cryogenic systems but to maintain extremely low temperatures for coherence. So imagine this is a layered system, hardware at the bottom, control and software on top, all working in a delicate harmony. Now let us discuss one by one key parameters which are going to use to build a quantum computer. First, let us start with qubits. Not all qubits are created equal. A good qubit should stay coherent for a long time, have high fidelity operations, which means very few errors, be easy to initialize, control and measure, and be scalable to thousands or millions of units. For example, superconducting circuits are fast but need deep cooling, whereas trapped ions are very accurate but slow, and photons work at a room temperature. It's good thing to hear, but are hard to store. But this is the goal, to find balance between the performance and practicality. Come to the quantum gates and circuits. In a classical logic, we have AND, OR, NOT gates, whereas in quantum computing, gates are unitary operations that rotate qubit state on the black sphere. See, the common gates are Pauli X gate is like a quantum knot. Hadamard gate creates a superposition, like our coin starts spinning. The C0 gate entangles two qubits. When you connect many of these gates together, we form a quantum circuits, which are building blocks of algorithms like Shor and Grover. Now, let's see what is quantum coherence and decoherence. Coherence means qubits retain in its quantum state without interference, like the ability of qubits to maintain quantum states. Whereas decoherence means a loss of quantum behavior but due to environmental interactions. That means the decoherence happens when a qubit interacts with its environment, like someone bumping the table while you are spinning a coin is still in motion. But to fight with the decoherence, that means to avoid decoherence, we need to isolate a system, need to cool down the temperature up to millikelvin temperatures and use the error correction codes. Means without coherence, means without quantum states, the quantum computer becomes just another classical one. That's why need to maintain the system should be always coherent. Maintain require environment which influence the coherent status leads to decoherence. Next come to the quantum error correction. In a classical computers, we can simply copy data for redundancy, but in quantum computing, we can't copy a qubit due to no cloning theorem. Instead, we encode one logical qubit into several physical ones using quantum error correction. For example, it's like a having multiple musicians playing the same tone. If one goes off, the others help to correct it without any stopping the song. Like that, this redundancy through entanglement allows us to detect and correct the errors without measuring the qubit directly. Means, in order to maintain error-free quantum computer, we need to incorporate quantum error correction. Now, let us see what are the hardware approaches. That means what are the various ways to realize qubits. However, different companies are experimenting with various realizations or physical implementation of qubits. Let us see the superconducting qubits used by IBM and Google. Trapped ions used by IonQ and Honeywell. The photonic qubits used by X01 Boson Q. Spin qubits explored by Intel and Dell. But topological qubits still theoretical, but it is promising high stability. Each of has its own strengths and weaknesses. Like, everyone is experimenting on all of them. It looks like different car manufacturers working on different car engines like petrol, electric, hybrid. Means all are trying to reach the same goal. That means reliable performance. That means which approach you are adopting, it doesn't matter. Need to verify which one is giving a reliable performances matters. Next come to the cooling infrastructure and control environment. Now students, this part looks like more like engineering than physics. Quantum computers need ultra precise control and extreme cooling. The qubits, especially superconducting ones, operates at near absolute temperature, just few millikelvins. That is even colder than outer space. We can use cryogenic systems, but to keep them cold and microelectronics to control their behavior. Whereas in trapped ion systems, lasers are used instead of microelectronics. So you can think the quantum computer is very cold orchestra. Each instrument means qubit must be play its note in a perfect harmony. Controlled by a conductor. That means controlled by a control electronics. Then only it gives the required performance. Let us emphasize how delicate this quantum computer is. If the temperature fluctuates even slightly, the qubits lost their quantum properties. It looks like imagine trying to hold a soap bubble steady in a wind tunnel. That means how hard it is to keep a qubit stable. So the cooling infrastructure acts like a productive environment for qubits, while the control electronics are brains telling each qubit when and how to move. That's why most quantum computers live inside large, shiny, gold-colored refrigerators called as a dilution refrigerators. This is one of the key infrastructure need to create to get the stable operation from quantum computers. Now, let us see what is the software and quantum programming. Now that we have covered the hardware, let us move to a software layer. Quantum computers need a special languages like C, Python in classical computers. However, they won't work on qubits. So we have to have tools like Qubits, Kit from Google, Bracket from Amazon. Some of the special languages we need to operate on qubits. Like think of it. It has a programming in terms of gate operations like telling qubits rotate by this much, then entangle with that one. In a real system, we often combine the both quantum and classical process. This concept called hybrid computing, where the classical computers help to manage the quantum workloads. That means may not be a completely classical computers, may not be completely quantum computers. You may have to make use the support of classical computers to run the quantum computers in future. Now let us go to the next topic, fragility of quantum systems. Okay, let us talk about why quantum systems are so fragile. As we discussed previous chapters, quantum computers are very sensitive, very delicate, which is rely on superposition and entanglement, are very delicate properties that collapse when disturbed. Even a teeny vibration, a stray photon or a small change in temperature can destroy these quantum states. It looks like if you consider an example like trying a balance to balance a pencil on its tip. That means any little breeze makes it fall. But this fragility is one of the main barrier to building a large quantum computers. Means we spend more effort protecting qubits than actually competing with them. But what is the reasons for that fragileness? What is the effect of that fragility on quantum states? Or one is the decoherence. Now let's dive into decoherence. It is one of the biggest barrier or enemies of quantum computation. When qubits are interact with its environment, its superposition collapses into a definite classical state. That means either 1 or 0. Let us consider an example. If photon bumps into a qubit in one state, but an interaction measures it unintentionally, but the superposition is gone. Mathematically, this is seen that the decay of diagonal elements in a system in a density matrix. In simpler terms, you can say like this: decoherence turns a quantum computer into my regular one. That's why isolation, error correction are so important to maintain my quantum states without affecting the my decoherence. There are two main types of decoherences. One is the dephasing, when the relative phase between the qubit 0 and 1 is lost. Then second one, amplitude damping, loss of energy from excited to ground state. That means when energy leaks from excited state to ground state, that may cause the decoherence. But what is the effect of decoherence is, which is reduces the fidelity of a quantum gates and limits the computation time. That means in order to maintain a coherence, we have to keep long coherence time. In order to extend the coherence time, we kill the qubits one way, or we can isolate them from the vibrations by applying quantum error correction. We can protect the information. Means we need to maintain quantum states by operating the quantum computer in low temperatures, isolating the quantum bits, and applying quantum error correction. Now another parameter is which is cause for fragility is quantum noise. Means now even if you manage to reduce the quantum decoherence by incorporating low operating voltages, low operating temperature, and proper isolation and applying quantum error techniques, we still face a quantum noise. Means that is random disturbances that affects the again qubit states. Some of them are amplitude damping, energy loss from qubit, phase damping, random phase shifts destroying the coherence, and depolarizing noise, random flipping and mixing of states. Now there are various sources which cause the noise or imperfect control signals, temperature fluctuations, electromagnetic interference, even neighboring qubits interactions called as a crosstalk. For example, if you shout in a pit room, your echo might disturb others. That's what crosstalk in quantum arrays. The types of quantum noise include thermal noise, gate noise, measurement noise, and crosstalk. But to reduce the quantum noise, my researchers proposed some techniques. They are noise calibration, means tuning the system to predict and cancel out the known disturbances. Pulse shaping, modifying the control signals to minimize unwanted effects. Dynamical decoupling, flipping qubits rapidly so that the random errors average out. And materials means reducing the defects in atomic level in a superconducting chips. Even you may feel that defects in materials may impact very small, but together they significantly extend the coherence and gives great accuracy. Let me summarize. The quantum noise might include a decoherence and all other random disturbances that mess up with quantum information. So we can never eliminate the noise completely, but we can mitigate it through clever engineering and software techniques. Modern computer processors like IBM constantly run the calibration routines, almost like self-tuning musical instruments to stay accurate. In the end, the quantum computers are not silent machines; they are noisy orchestras that must be continuously tuned. Finally, to wrap up this section, the quantum control is a art of the precisely steering qubits. Our goal is to apply gate operations with incredible accuracy, often with errors less than 1 in 10,000. However, to achieve this much accuracy, we have a control challenges which include maintaining timing and synchronization, balancing isolation with accessibility, scaling up control system as qubit numbers is growing day by day. However, we can improve the accuracy by adopting some of the approaches include microcontrol for superconducting qubits, laser control for trapped ions, and even you can incorporate machine learning based calibration to adaptive control. It looks like a need a precise control over a quantum computer like a spacecraft through a turbulence. We need a perfect control, precise timing and constant correction. Then only the spacecraft will move to the specified orbit or target orbit. Like that, the control should be a very precise timing and constant correction to achieve our goal. Let us discuss about the precise requirements. Now let us look that is precise and timing. Quantum gates must operate with nearly perfect accuracy. Even a small error can propagate and run enter the algorithm. It's things like a tuning of guitar. Even if one string is slightly off, the whole song sounds wrong. That means each and every bit should be error free. Otherwise, it will spoil the whole quantum operation. Let us come to the timing point of view. But timing is very very important factor because quantum operations have to be perfectly synchronized. Remember, the decoherence is always taking in the background like timer. That means if there is even a slight delay or jitter between the signals, qubits lost coherence and correlations will disappear. So, engineers need to design a control electronics that works in nanoseconds with ultra stable clocks, which leads a precise and timing are literally what keep a quantum computer in tune or in a right manner. Next, isolation. This is a fascinating paradox. Qubits must be isolated from their environment to avoid the decoherence, but at the same time, we need to access them to control and measure their states. It's very hard situation. Like trying to a pet a butterfly without making it fly away. That means too much interaction causes the system gets collapses. Then come to scalability is concerned. As you move from few qubits to thousands or hundreds, it becomes exponentially harder to maintain uniform control and prevent crosstalk between the qubits because every new qubit adds new control lines, new timing issues, and new noisy sources. This is one of the biggest engineering challenge in quantum computing today. Let me summarize. What are the various sources of fragility in quantum systems? What it means, what is impact on the system, what is various ways or techniques to overcome, like decoherence that causes the collapse of quantum state, that limits the speed of operation. However, we can improve or we can avoid the decoherence by adopting isolation techniques and error correction techniques. As per noise is concerned, there is a random errors distribution of disturbances. It reduces the overall accuracy of the system. However, you can improve or you can decrease the noise by filtering and decoupling and using the new materials. Lastly, control errors impact the imperfect manipulation. Causes the gate becomes infidelity. By applying calibration and better hardware, you can overcome the control errors. That is about the fragility of quantum systems. Now let us jump into the conditions for a functional quantum system. Alright, now we have seen how the delicate control is. Let us summarize what functional computers must have to maintain a proper operation with good accuracy and reliability. These are the four conditions are absolutely essential. First one is the isolation, which protects qubits from environment. Error management, correct the inevitable errors. Scalability, build a larger systems efficiently. Stability, maintain reliable operations over a time. If one of these fails, the entire system becomes unreliable. Let's look at each of these conditions in detail. Now let's consider the isolation. Isolation is the first and most fundamental requirement in quantum computers. Yes, quantum states are extremely delicate. That means any unwanted interaction with the environment can collapse the qubit state. So, we shield the qubits from heat, electromagnetic fields, vibrations, and even stay cosmic particles. For example, in case of quantum, superconducting qubits are kept in near absolute zero using cryogenic systems, and trapped ions are elevated in a vacuum chambers using electromagnetic fields. But for better isolation, might suggest for longer coherence time. That means how long qubits stay in quantum means is a coherence time. Now let us see error management. Even with this best isolation, my errors are unavoidable. We need to error management. Generally, the quantum errors come in two main types. That is bit flip, pair 0 turns into 1 or vice versa. Phase flip, where the phase relationship between the 0 and 1 changes, where now in classical systems we can copy and check the data, but in a quantum systems we can't do it. That means no cloning theorem permits the copying of writes. So scientists use the quantum error correction techniques like shard code and surface codes to encode one logical qubit into several physics ones. But this one is very essential because a single uncorrected error can marine the quantum computation. That means that will affect the overall system performance. That means we need to adapt a special techniques to maintain error management in case of quantum system. Let us come to the scalability as the qubits. The number of qubits to implement any real-time applications is required more and more. Right now, most of computers have fewer than qubits, fewer than 500 qubits. But to solve the real-world applications like drug discovery or climate modeling, we needed thousands of, even millions of qubits. That means scaling up. That means the scaling up is necessary. What the scaling up involves? Building a large, it's not only adding more qubits, but also adding more connections, cooling and control channels. It faces the both hardware and software challenge as like imagine going from tuning 5 musical instruments to managing full orchestra of 1,000 players. Just imagine how complex it is. That means you need to maintain all the factors that may not be the adding of number of qubits. In connection with all of them, you need to maintain all the requirements to control the overall performance of a quantum system. Let's come to the another important factor, that is stability. Is about making sure the quantum computer performs the same way, that is today, tomorrow, next week, and so on. That should give a stable output. That means it is a long-term reliability of qubits, gates, and control system. Now, what is the various reasons to become unstable is if coherence times or gate fidelities fluctuate, we can't trust the results. So we need to consistent calibration, low gate error rates, qubits with built-in robustness are required to get a better stability. For example, the topological qubits which are being researched by Microsoft and designed to be inherently stable, without stability, the quantum system cannot scale or run complex algorithms. It's like trying to build a supercomputer with necessary requirements. If you combine all together, like the isolation prevents the decoherence, error management corrects the mistakes, scalability expands the system capacity, stability ensures the consistent performance. These four are deeply connected. That means improving isolation helps the stability, better stability supports error correction, and effective error correction must be scaled with the number of qubits. If anyone fails, the entire quantum system becomes unreliable. So the designing a quantum computer is like a balancing 4 spinning plates. You can't afford to let even on one drop. That is scale of complexity included designing a quantum system. Now let us see the next topic. What are the theoretical barriers in quantum computing? The physics challenges that make a quantum computing is so hard. Let's have a look at what are the major challenges we have as per physics is concerned. First one is maintaining entanglement. Next one is the implementing error correction efficiently. Like if you recall the definition of entanglement, it is the special link between the qubits which allows them to work together like a single system. Without it, we lose the quantum advantage. But unfortunately, the entanglement is incredibly fragile. On the other hand, the quantum error correction is mathematically complex. It requires huge redundancy and precise measurements without collapsing the state. These are the two mountains that quantum researchers are trying to climb as on today while building a quantum computer. Now let us see one by one, like entanglement is concerned. In case of, as per entanglement as definition is concerned, when the two qubits are entangled, their status are linked to each other. That means measuring one instantly reveals other state. Even they are in far apart. That means how long the distance separate is doesn't matter. However, the concept entanglement is heart of many quantum technologies like quantum teleportation, quantum gates, quantum error correction, and speed of the algorithms like Grover and Shor's. That means we need to maintain the entanglement is plays the vital role in quantum systems. But as I mentioned, unfortunately, it is a fragile. Let us see what are the sources we have. The entanglement becomes fragile. Like it's so bubble So bubble, it can be easily destroyed by even the thinnest disturbance. That means it's very, very sensitive like a soap bubble. That may destroy due to a small or teeny disturbances. Let us see what are the various sources which causes the fragility in collapsing, fragility in entanglement. One of the foremost one is decoherence. This is due to interaction with the environment like photon interaction, light or thermal interaction like vibrations may cause the decoherence that may collapses the entanglement state. Noise, even tiny temperature, electrical and vibrational fluctuations can ruin the correlations. Scaling, as more qubits are try to entangle, the more complex and unstable the system becomes. One last one is the measurement problem. Any unintentional measurement breaks the entanglement immediately. So in practice, entanglement is just as hard to create. It's even harder to preserve. But that's why much of quantum engineering today is about keeping the bubble from popping. Now let's see what is the need of error correction in quantum computing. As you discussed in the previous slides, the errors may be due to any reasons. Maybe one of the reason is decoherence. But in the case of classical computers now, we handle errors easily because we can copy the bits, use the parity checks and correct the mistakes with redundancy. But in quantum computing, the situation is very different. We can't copy qubits because no cloning theorem, and errors come in more flavors like bit flaps, phase flip, or both. And also, qubits are constantly being disturbed by decoherence and imperfect gates. So we need quantum error correction to protect information without measuring directly. The solution is quantum error correction codes. They use entanglement and indirect measurements called as syndrome measurements. The question is, how can you correct the qubits without measurement? Here is a $1,000,000 question, because if you measure the quantum state, collapses it. How can you check the error? How can you check for errors without destroying it? The solution is quantum error correction codes. They use entanglement and indirect measurements called as a syndrome measurement, in which you don't measure the qubit itself, you measure the related properties that reveal if an error occurred. For example, a logical qubit might be encoded into 7 or more physical qubits. If one goes wrong, the others vote to correct, all without collapsing the superposition. It looks like a group of friends whispering about the mistakes without directly confronting the version. That means the problem is fixed quietly. Then the conversation continues. That leads the incorporation of quantum error correction codes. It leads the higher grade. Till now, we understand the theory of the quantum systems. Let us see how these ideas come to life in real hardware. As you know, the qubits as a basic unit for information of quantum systems. But to build in real world applications, we need a physical system that behaves like a two-level quantum state. There are different platforms use different physics to realize the qubits, like superconducting circuits, trapped ions, photons, spin qubits, and topological circuits. Each platform has its own trade-offs in terms of coherence time, gate fidelity, scalability, and etc. That's why different companies using different platforms. Like IBM using a superconducting circuit, IonQ using a trapped ions, like that. Let's start with most commonly used approach, that is superconducting circuits to realize qubits. First, let us see the basic idea behind this. These bits are essentially artificial atoms to build from electrical circuits that behaves quantum mechanically. This operates in very low temperature. They rely on superconductivity where the resistance drop to zero, and the Johnson junctions which create a non-linearity needed to discrete energy levels. In simple terms, there are tiny loops that metal that can hold current in two directions. One is clockwise, another is anti-clockwise directions, or positive or negative directions, which mapped with the zeros and qubits. We can control them. The behavior of the current direction can control using microwave pulses, just like radio frequencies controlling an antenna. Let us understand the physics behind this quantum superconducting qubit. It behaves like a quantum harmonic oscillator that can have many energy levels. Now we need to add the Johnson junction. Then the potential becomes non-linear, which allows us to isolate just two levels, that is ground state and the first exit state. One belongs to 0 state, another belongs to 1 state. It is essentially use the electric charge, magnetic flux as a quantum variables and the circuit becomes Hamiltonian, defines the energy levels. By carefully designing the junction parameters, we can tune the qubit frequency and behavior. Then we can make use these bits as a quantum bits, that is qubits, for various applications. But just like a position and momentum in mechanics, that means solving Hamiltonian gives us the discrete energy levels. That's what allows circuit behaves like a quantum atom. Based on the charge and flux, the superconductors classified into three categories. That is the charge qubit, flux qubit, and phase qubit. Sorry. Now let us see what is charge qubit. These things are we detailedly discussed in chapter 2. This is one of the earliest designs. It is small conducting island connected to a reservoir through Johnson junctions. The pairs of electrons that move together can tunnel one onto off the island. By applying gate voltage, we can control the qubit's quantum state. Similarly, let us see the flux qubit. Here the superconducting loop interrupted by the Jasper junctions. The current can circulate clockwise or anti-clockwise. Two directions represent 0 and state and 1 states. By applying external magnetic field, we can control the energy difference between the two states. Next, phase qubit. Here, bias current applied to the Jasper junction, creating a tilted potential as well. The Q states are discrete energy levels within that well. Similar to how the ball can occupy the different rungs in a tilted bow. By changing the bias current, you can control the spacing between the energy levels. Then what are the advantages of the qubits? That is superconducting qubits are they have very fast gate speeds. That means operations happen in a few nanoseconds. They are compatible with existing microfabrication techniques, meaning we can use the same technology as a computer chips, and they can integrate easily with the classical electronics. On the other hand, they have challenges. They must operate in ultra low temperature, requiring complex and expensive cryogenic setups. They are prone to decoherence due to material defects and electromagnetic noise. Scaling adds up more wiring, which creates a new heat and interference problems. So superconducting circuits are currently leading, but not perfect. Still, race is still open. Next, go to the trapped ions. One of the most elegant information implementations. Here, the individual ions, the charged atoms are suspended in electromagnetic fields inside the vacuum chamber. We use the laser to manipulate their internal energy levels, which present as a qubit state 0 and 1. Each ion can thought a perfectly identical little atom, nature its own qubit. For example, many systems like use yttrium and calcium ions or behaves as a ion medium. The beauty of trapped ions is that they have very long coherence times, sometimes lasting seconds and even minutes. It's like having a memory that almost never forgets. Now let's see what are the advantages of this. It is extremely long coherence time, that is maybe seconds to minutes. High fidelity gate operations, that means very accurate. All ions are identical, so they have no manufacturing variability. On the other hand, it has challenges that gates speeds are low as due to long coherent times. That operation like milliseconds and compared to nanoseconds in superconducting circuits. Laser control systems are complex and require a precise alignment. Scaling to hundreds and thousands of ions difficult to make use the need of stable optical steps. In short, trapped ions are perfectist, slow but extremely precise. Next, photon as a qubit, in which you are using the polarization as a qubit. Photons particles are light. They have perfect carrying information over a long distance. So while superconducting qubits are great for computation, the photon bits are ideal for communication. We can encode the quantum information in several properties like polarization, path, phase, etc. For example, a single photon traveling through one of the two paths can represent 0 or 1, and the superposition of these paths can be represented in quantum states like this. One of the most common ways to encode the qubits are light through a polarization. That is, vertical polarization leads 1, horizontal polarization leads 0. We can have a look on the black circuit. Now let us see what are the advantages of photonic implementation of qubit. They are operated at room temperature. That means no cryogenic needed. This is one of the beauty what I observed in photonics as superconducting working at very low temperatures. They are very fast, traveling at speed of light as you are using light as a. They expect is very little decoherence. Photons rarely interact with each environment, but their big challenges are photonic gates are problematic. That means it's not a deterministic. That meaning they don't have always work. Photons lost imperfect detectors, making scaling difficult. It is hard to make a photons interact with deterministically. They usually just pass through each other. So while photonics is perfect for quantum communication and networking, we're still working to make a variable viable for quantum computing. This summary of the quantum implementations and comparison between the different realizations with respect to physical qubit, operating temperature, gate speed, coherence time, scalability, maturity, and examples means which company is using this technology. Now let's jump into the what is the vision. That's what we are expecting with respect to quantum computers. What is the reality? As you know, the quantum computing aims to break through in cryptography, materials, and AI optimization and security communication. Let us see one by one. As per qubit count is concerned, we are looking for millions of qubits to apply the quantum system in a real world applications. But as on today, the reality is we are able to implement or we are able to realize hundreds of qubits only. Come to the error correction is, instead we are looking for a error-free device, but still theoretical approach, still yet to resolve so many issues compared to error detection. As far as speed is concerned, we are vision is as compared to classical computers, it gives the thousand times of the classical computer speed, whereas only we keep as far temperature is concerned, we are looking for the system should work at room temperature, but it need nearly absolute zero temperature. Applications is concerned, like as classical computers, we are looking for the universal computer that should use for all kinds of applications. Whereas reality is concerned is limited and still in experimental. Cost, vision that should be widely available like classical computers, but as of today, the quantum computers are in research led only. This is one of the big challenge. Like last one, but the role of quantum states, role of quantum computer, quantum software to controlling the overall quantum system. Even with all these hardware challenges, software plays the huge role to bridging the gap between theory and practice. Quantum software translates the high-level algorithms into exact gate operations that hardware can perform. Might also holds a nice management, error mitigation, and optimization of gate sequences. But the softwares like QSIT, Ocean allows researchers to and students to write just a quantum programs even on simulators. These tools are what make the quantum computing accessible. You can experiment with the qubits from your own laptop today. As quantum computers grow larger and software will become a brain that keeps everything synchronized. It will be manage error correction, translate complex algorithms into optimized circuits, allocate resources like qubits in memory, and coordinate a parallel control across it. So in the near future, software will join, just assist the hardware. It will orchestrate to it. Just like how the operating system manages all the components in a classical computer, quantum software will ensure the coherence, timing, accuracy in real time. So the key to quantum computers from lab experiments to practical mission. Thanks for watching. Thank you very much. Have a nice day.